Okay, we're going to spend quite a bit of time finding volumes of solids of revolutions using mostly using what we call the disk method and the washer method. And then we'll move on to what we call the shell method. So disk and washer method are really the same thing. I'm going to talk all about disk method in this, and then washer is just kind of a generalization of that. Washer method uses Y's instead of X's. It's completely a different approach. These are all for what we call solids of revolution. So the idea here is we're going to have some curve in the XY plane, some Y is a function of X for the moment. We'll go the other way and do X as a function of Y later on. But for the moment, so let's say for now, Y is some function of X. That's my curve right there. Now I'm going to take that curve, shade in the area between that curve and the x-axis, and then I'm going to take that whole region and rotate it around the x-axis. So imagine that I've literally built this. I've built this shape here out of a piece of paper, and I rotate that around, and I want to fill in everything that gets swept through. We would end up with this shape that looks like this volume. So we're taking some curve, rotating it around, and then filling it in with water. And this would be some starting point. Maybe we'll call that A. And this is some ending point. These are X values. In this case, when we're rotating around the X axis. Okay, so let's just kind of take a look at what we're doing here. This is called the disk method, which I'll talk more about in a minute. So I've got some function. I've got some bounds from x equals 1 to x equals 4, and I'm going to take that and rotate it around the x-axis. So I only care about this region here from 1 to 4, and I'm going between the graph and the x-axis, and now we rotate that around the x-axis. So this shape here, and I'll try to draw it. We're going to end up with it's going to be symmetric here on the bottom. I am really bad at drawing these. Ooh, something like this. I did not do a very good job drawing it. We're rotating this around. So you can see better here. We've taken this and rotated it around. So we get this horn looking thing. We're going to find this volume. And what we're doing in the background is we're doing a Riemann sum. We are breaking this guy up into a bunch of little cylinders of thickness delta x. Each one of those cylinders will have volume, the cross-sectional area times the thickness. The thickness will be delta x. So if I come out here to some random x value, I'm at x, maybe let's call him xi. Then the volume at little xi there will be approximately equal to the area at xi, the cross-sectional area, this area right here, times the thickness of that little cylinder, delta x. We're going to add up all of these, so the total volume will be approximately equal to the sum from I equals 1 to n of all these little VIs. So we're going to break this guy up into n. We're not really doing this, but in the background, we're breaking this up into n little slices, what we might call disks. Each volume is the cross-sectional area times delta x. The total volume then is, I'll add those all up. Then we take the limit as n goes to infinity of the sum I equals 1 to n a at xi delta x. Taking the limit as n goes to infinity literally means the same thing as taking the limit as delta x goes to 0. This will turn into an integral from our start to our end of a of x. That's not times x, that's a of x dx. Okay, so at some spot x, so I come out here, here's some spot x. What is this cross-sectional area? My cross-sectional area on the solids of revolutions. Your cross-sectional area is always a circle. Always. On these kinds of problems. On that pyramid problem we did in the other video, it wasn't, but that wasn't a solid of revolution. In these problems, when you rotate something around, your cross-sectional area is always a circle. What's the area of a circle? Pi r squared. What's r? R is that distance right there. That's just the function height. R at, which is a function of x. I'm going to write that. R depends on x. And that's always just going to be your function value at x. See right here, this circle has a different R right there. What's that R? Oh, that R is just the function value. It's just that distance from the x-axis up to the curve. So your cross-sectional area is always pi r squared, but that's always pi f of x squared. So volume is the definite integral from a to b, your start to your end. Remember, they gave us those. Here's a, here's b. Cross-sectional area is always pi r squared, which is pi f of x squared. Dx. So like you can work through all the details here yourself. Here's f of x squared, and they've gone through the trouble squaring that out. Now we just integrate that. Again, you can check all these details. We're going to evaluate that integral from 1 to 4, and our final answer is 78 pi over 5. Okay, so this is called the disk method. And I spent some time Googling. I couldn't find great images of the disk method. I know they exist out there, but I couldn't find any. So the idea is you've got some curve, you rotate it around, and what we're doing in this method here is we're approximating that volume by imagining this blue volume here as a bunch of coins stacked on top of each other, where those coins are changing size as you go. The radius of each coin at some position x is just the function value at that position x. Then we take the limit as delta x goes to 0. So this is delta x, the thickness of each coin. That's equivalent to saying we're taking an infinite number of coins that are all infinitely thick. And as the number of coins goes to infinity, as the thickness goes to 0, this volume will approach and eventually at infinity equal this volume. So here's the general formula. The disk method formula, you're going to learn a bunch of different formulas. You're going to learn the disk formula, the washer formula, the shell method formula. Those are all when you go around the x-axis, and then you're going to learn 3 new formulas when we rotate around the y-axis. Then you're going to learn more formulas when we rotate around a random axis. And I'm telling you, if you just think, oh, I'm going to memorize all these different formulas, I've been doing this for over 20 years. I don't have any of these formulas memorized. I would not be able to do these problems if I just memorized formulas. You have to understand the process. That's why I'm spending so much time talking about what's going on in the background, that we're really building a Riemann sum. That's the way you want to think of this. If you try to memorize formulas, you're going to have a bad time. But this is the general method. If you want to memorize something, this is what you would memorize. So you've got some shape, some curve, some f of x. Ooh, it could look like whatever. You're going to rotate that around. And I'm going to draw a bad picture here, but bear with me. We're going to take that and rotate it around all the way. So that one should be a little bigger. That one should come out a little more. This one should come in a little bit. I'm going to try to draw this. I'm trying to draw the reflection of that. I didn't do a very good job, but I think you can see what I'm doing. This volume, when we've taken that shape and rotated it around the x-axis, this volume is, here's my starting, here's my ending, the definite integral from A to B, the cross-sectional area at X, because that area right here, that area is going to depend on where you are. This cross-sectional area is smaller than this one is. Dx. Okay. And here we're doing f of x equals square root of x. Okay, so we're going to use this method to find the volume of the solid of revolution obtained by taking y equals square root of x. We're going to rotate it around the x-axis from 0 to 9. So I've got this picture here. Here's my function. I'm going to rotate that around the x-axis. Again, what's going on in the background is we're stacking up a bunch of these disks. So imagine I've got that disk and that one and that one, and these are all lying on top of each other. They're not overlapping at all. I'm adding all these little disks up. Each of these is just a little cylinder. Now, it's really not, because see, the sides aren't perfectly square. But if we pretend that they're square, then the volume of this guy is just area of the base, which is a circle, times the height. The height is dx. Okay, so drawing this guy out here, we got square root of x from 0 to 9. We're going to rotate that around. I think I could draw it better. Your bottom is always going to be a reflection. Like if this is f of x, this will always be negative f of x. If you're trying to draw these out, here's f of x. When we're rotating around the x-axis, it's always going to go from f of x down to negative f of x. Okay, so we pick some random spot x here. I need to find the cross-sectional area, this circle. Imagine this is the 3D picture I'm drawing here. This is coming out at your eyeballs. So this guy has rotated around this cross-sectional area here. Remember, this is y equals square root of x. That cross-sectional area, that's just a circle where this radius here let's call it r, that distance is just square root of x. Remember, the cross-sectional area is always going to depend on x. It's a function of x. Then the area of that circle, it's a circle. It's pi r squared will be pi square root of x squared. So just pi x. Then this volume will be the definite integral from 0 to 9, because that's what we were told. I'm going to write this out again. A of x dx. So definite integral 0 to 9 pi x dx. Now we just do the antiderivative. The pi just comes along for the ride. I can just pull it out. I didn't have to write this as a separate step, but remember, constants can come out front. So that's pi x squared over 2 evaluated from 0 to 9. At 0, everybody's 0. So we just plug in the top, we get 9. So what is that? 81 pi over 2. And our units here would be units of length cubed. So if we were told, for example, that f of x here is measured in meters, so let's say, for example, in meters, then this would be meters cubed. And that's a good place to stop.